if our system of inequalities does not create or form a closed region, we then have what is called an unbounded region. And so here we're going to look at a couple of examples of such. Just graph the system of inequalities, name the coordinates of the vertices of the feasible region, find the maximum or minimum values for the function of this region. Now, we got one fairly good clue as to why this would be an unbounded region. If you look right here, both of those inequalities have the same slope. And we know that if we've got the same slope, we've got parallel lines. And parallel lines are never going to cross each other. So that's a pretty good clue. This is going to be an unbounded region. Now you can see over here that I've put the inequalities into the calculator. We've got y is less than or equal to 8. And y is greater than or equal to negative x plus 4. And the third inequality is y is less than or equal to negative x plus 10. And once we find the vertices that we're going to have, we're going to plug it into this function, and then we're going to determine, do we have any maximum or minimum values? We're going to have one. But here's the tip, we're not going to have both. So let's go here to the next slide. And here you can see that I graphed these. And our region that is in common, let me see if I can get a color that'll show up. Let me try this. Is right in here. Now, up here I've got a vertices. And here I've got a vertices right here, right in those areas right there. And let's see, looks like negative 1, 2, 3, 4. When x is negative 4, y is 1, 2, 3, 4, 5, 6, 7, 8. And when x is 2, y is also 8. Now, I put up the table here because sometimes it's hard to see. It gets messy on the calculator when you've got all these regions being colored in. And what I'm looking for is, where is there a value of x that I see two of these functions actually have the same value, in other words, y. And here I can see and confirm that right there at negative 4, both y1 and y2, the first and second equations, are both equal to 8, and which is what it appeared that when I looked at the graph. And also right here, when x is equal to 2, I see that y1 and y3 are also both equal to 8. And that's confirming my vertices. So I've got vertices then here at negative 4 and 8, and then we've got another one at 2 and 8, and we're going to plug those x and y values into this function of x and y, xy, which is negative 6x plus 8y. All right, so let's see. Let's do. So we got negative 6 times negative 4 plus 8 times 8. Negative 6, negative 4 is positive 24. And 8 and 8 is 64. And 24 and 64 is 88. Let's do the second set with the 2 and 8. Then we'd have negative 6 times 2 plus 8 times 8. And negative 6 times 2 is negative 12. 8 times 8 is 64. Negative 12, 64 is 52. So we have a maximum at 88. Why do I say maximum? Because if when I'm coming down in this direction right here, it's going to negative infinity. It's just going to keep going on and on. So I'm not going to have a minimum. I'm just going to have a maximum. And so then we could say that we've got that at -4, 8, we have a minimum, which is equal to 88. And there is no, excuse me, that's a maximum, not minimum. Maximum at 88, and we have no minimum. Let's take a look at one more. So again, I've got three inequalities. Y is greater than or equal to x minus 9. Y is less than or equal to -4x plus 16. And y is greater than or equal to -4x minus 4. And once again, I see that in two of my inequalities, I'm going to have the same linear slope, and we're then also trying to determine the value. And you can see over here on the right that I've entered those into my calculator, which creates this graph. And again, my area of my unbounded region is coming in right here, and it looks like I got a vertex right there, and I've got a vertex right there. And let's see, that looks like what, +1 and 1, 2, 3, 4, 5, 6, 7, 8, 1, 8, and 1, 2, 3, 4, 5 at 5 at, that's -8, by the way, not +8, and 5, -4. And again, when I look at my table, I see that when x is 1, I have two of the y values that are the same, and when x, which is -8, and when x is 5, I also have two y values that are the same, but in this case it's -4. So my coordinates of my vertices are 1, -8, and 5, -4. Now again, if I'm looking at what's unbounded, I can see that it's headed up this way. So I'm going to already know that I'm not going to have a maximum, I'm just going to have a minimum, but let's find out which one it is. So let's see, I got 10 times 1 plus 7 times -8, and 10 times 1 is 10, and 7 times -8 is -56, and 10 minus 56 is -46. And then for the 5, -4 coordinate, we substitute there. We got 10 times 5 plus 7 times -4. And 10 times 5 is 50. And 7 times -4 is -28. And 50 minus 28 is 32. And so I've got a minimum right here. So at 1, -8, we have a minimum, which is equal to -46, and we have no max. All right, unbounded regions, linear optimization, a lot of business applications to be used with that. Maybe you'll take a finance calculus class one day. One of my former students told me they took that last year.